Okay, we'll just go ahead and run the Fibonacci sequence because I know that works. Okay, so another Fatstacks video. I understand that I haven't posted a video in a while, truth be told. It was mainly because I was working on part 4 of the tutorial series, and that takes quite a bit of effort, and doing that on top of all this means that video output kind of slows down a little bit. So I'm kind of rushing this. This really isn't a polished product here that you're seeing, but I at least want to get something out to you guys so that you guys don't think I've abandoned you, uh, because I am working on this stuff pretty hard. Uh, and hopefully, it's probably going to be a while before part 4 comes out, but nonetheless, it is on its way. But in today's video, I mentioned in the last video that I was going to try and work on the I/O ports. Here they are. It sort of works. The output works anyway. I'll get to how it works in a sec. The input, not so much. I'll also get into how that works in just a sec. But before I do want to mention a user, and I neglected to apprehend their name once more, but a user mentioned that my footage is very, very low quality when it comes to the all-iron world, and I'm inclined to agree with him, because having the grid that slowly gets closer and closer together as it goes out into the distance is hell on compression, especially on YouTube, so it lowers the quality drastically. So what I've effectively done is I've just installed a small, very small resource pack, and when I say small, I mean it just modifies one image, and that's the iron block, to make him just a little bit softer. So this should look better in the final product, hopefully. I've also done some tweaking with shaders, tweaked the anti-aliasing a little bit, and I've also added Optifine. In fact, I can't remember which button's my zoom. That's the Z. Okay, I've set it to Z. But I've added Optifine, and so that should help a little bit with the quality of the footage a little bit. And then whilst I was in there, I also added high contrast lamps so that you can properly tell what's on and what's off. Because let's be honest, the default texture, you really can't tell what's what. It's just too close together. But enough rambling about random stuff. What you're currently seeing is the output. We've got the input over here as well. And right now we're just running Fibonacci. So the Fibonacci program was already programmed to use the output. And so what it was designed to do is it was designed to run its algorithm, and after every iteration, output its result to the I/O. There was never any I/O connected, so we never actually saw that output. We were basically just looking at what was going on in memory with the popped stack here, because the popped stack would actually show exactly what was going on. You could actually see the pattern. Granted, it was duplicated, so you get 2 of every number, but you get 1, 1, 1, 1, 2, 2, 3, 3, 5, 5, 8, 8, 13, 13, and so on and so forth. Now we actually have an output, and the way this works, I tried to make this as similar to the intended output as possible. So what Endersight's stackish language does is every time you push out a character, it gets pushed across the screen. So you never lose characters. It basically just builds off of the string. And then once the clear screen command is initiated, that's when the screen is cleared and your data is lost. But other than that, it's effectively pushed. We're not dealing with characters, we're dealing purely with numbers, so I figured we won't have to deal with converting it to numbers or anything, but we will want to be able to see sort of a stack grow. So that's what I've got right here. Right now you can see there's a 1 at the bottom. Eventually it's going to get to the point where it's going to push out another number, hopefully soon here. And what's going to happen is this number is going to get pushed to here, and the new number is going to get pushed into there. Oh, just happened. So 1 just got moved up, 2 just got pushed in, and there's basically 16 slots. So that means we can store up to 16 numbers, and they'll all basically make their way up the display as they're pushed into the I/O port. And I'm liking the way it looks. I'm not liking its orientation, but there really wasn't much I could do, because I wanted to try and keep the least significant bit on this side. But if you were to actually look at the computer from this angle, the least significant bit is on this side, so it's kind of backwards. I could have put it like this, but then we wouldn't have easy access to the input. Now, I mentioned that this isn't exactly a polished product, and for good reason. The input isn't functional yet. I tried, I really did. I think I messed up the logic somewhere, and in fact, actually, just before recording this, I thought of a better way of doing this, and I'll probably go into details on that, but this was the intention. The intention was that the IO, or the in command, could bring in up to 16 characters. Where are those 16 characters going to be loaded? They're going to be loaded in a buffer. And so basically the user can asynchronously load the buffer with with their input, and the computer will then bring the data from the buffer as it needed it. Now, if the buffer was empty, there is this logic back here, which is responsible for this, but if the buffer was empty, a wait signal would be generated, and that would go into the CPU, and anytime the CPU entered state 23, which was the in command, it would first check to see if the wait signal was on, and if it was, it would remain in state 23, and it would never actually bring in the data until the wait line went low, at which point it would move to state 24, where it would actually bring the data in and push it over to the stack. And there's also some extra logic as well. So, for example, because there's only 60 entries, we can only enter 16 bytes of information at any given time. And if we happen to fill up the buffer, meaning we've put in 16 entries and the computer hasn't read any yet, then the write line will actually be disabled. So it's kind of just a capacity safety precaution, I guess. So the computer can't read from it unless we've put data in, and if the buffer is full, we can't put data in until the computer reads from it. So hopefully it never reaches a catch-22 situation where it never actually reads, but it's highly unlikely. And we've already pushed the third number in the Fibonacci sequence onto the display, which isn't too terribly interesting because right now it's just going 1, 2, 3, but eventually we'll start getting more interesting numbers, 5, 8, 13, 21, so on and so forth. Right, so what's wrong with this I/O port? Well, it's primarily, everything works fine except the wait line. So what's supposed to happen is you write your data, the computer reads, and the data goes in, and then immediately afterwards, if the buffer is empty again, the wait line goes back up. That's not what happens. What happens is the computer reads, and almost immediately, as a result, because the buffer is now empty, the wait line goes right back up, and the computer gets stuck in state 23. So that's kind of a problem. Like I said before I started recording this video, I actually came up with a solution for this, and it kind of ties into how this whole thing works. Basically, there are just two counters. And so they don't exactly move up or down, they just keep going up. So this one is for the right, and so every time you push the button, it changes it increments the counter, and a new one of these edge detectors goes down. Which means the previous one goes up, which it means it writes to that location. But as it progresses, once it gets to 15, it basically just rolls over and goes back to 0. So there's really no end to that. And then the same thing applies to the read register. It also just completely or just counts up constantly. And so to get the conditions that we're looking at, what we basically do is we compare those two values together. And so one of them compares them directly. So if they're equal, it creates a signal, and I believe that signal disables write. So if the two are equal, then that means the buffer is full and it disables write. There's another comparator which ties into this adder, and there's a reason why I used an adder for this counter rather than just using one of these counters. And that's because we're also comparing this value to this value plus 1. So this counter is basically configured as an incrementer, and it just feeds back into the register, so every time we clock this register it increments. But then that plus 1 value also goes into another comparator, and that signal is designed to disable the read line and also generate the wait line. So that's basically how it works. I'm not 100% sure because I haven't really thought this through, but I think if I just replace both counters with counters like these, and instead of having all this complicated comparator logic to generate the disable lines, I think what I'll do is I'll actually just have an increment or decrement register. And then every time I write to it, I increment the register. Every time I read from it, I decrement the register. And the idea is basically if the register is 0, the buffer is empty and we disable read. If it's 16, the buffer is full and we disable write. And theoretically, if I get the register to latch at the correct timing, it should mean that the wait signal would be generated at the correct time. And it would also make the logic a lot smaller because obviously this is quite messy. And I try to make this as clean as possible, but still I'm not too terribly happy with this, especially considering that I put like all this effort into making the computer itself nice and neat. So it's small details, but nope, we got more numbers on the Fibonacci sequence. 2 more, no less. How long have I been talking? 11 minutes. Yeah, so it's, it's not the most polished thing. I do intend on redoing this, but I figured for now I do want to get a video out. I was kind of hoping this would be the last one, but I think we're probably going to have one more video before I have a release video. But yeah, and then I think as far as updates from the last video is concerned, I made some changes to the timing. I don't know if it was too terribly beneficial though, but basically all of these lines are synced. So all of these lines will change their state at the exact same time as each other. Nothing too terribly fancy, but it did allow me to shorten the disable, I think it was this one, the disable time up here. So now it's down to like 3 ticks. Didn't really make much of a difference on the clock speed, but that's okay. I only expect the clock speed to get slower at this point because I've already done all the optimization that I can do in the CPU. And as soon as I add the RAM, the Redstone RAM, to the back of this, it's only going to get slower, even more so when we start accessing things towards the back. So that's something to look forward to. Yeah, other than that, I think this project is coming along quite nicely. Yeah, I think after this I'll probably spend a couple more weeks just trying to polish up the script for part 4, and I should be ready to start recording for all that, hopefully. But yeah, like I said, I am working on that, and I'm really excited to get that out to you guys. But I'm rambling, nonetheless. So that's basically just a small 12-13 minute update of the Fatstacks computer. Like I said, it's coming along quite nicely, and hopefully we will see the end of this project fairly shortly, because I think this project's gone on long enough. Nonetheless, I think I'll see you guys in the next video then.